Hi, welcome to the portal. In this video we are going to talk about the Doppler effect. So we are going to do more examples on calculating either frequency, velocity, either frequency or velocity, or wavelength at some point. So now remember, on the previous video we've calculated the frequency observed by the listener. Okay, so now we have a statement here. This is example number 2. Okay, so now it reads as follows: a police car moving at an unknown constant velocity past a sound detector placed at a station is emitting waves of frequency 380 Hz. Assuming the speed of sound in air is 340 meters per second. So now here we are seeing that the police car is the one that is moving. It is moving at an unknown velocity. Okay, so it's moving past a sound detector which is placed. So the sound detector, its velocity is 0 and the velocity of the car is unknown. So now the speed, the frequency of the waves that are being emitted by the police car is what is 380 Hz, right? 380 Hz. Okay, so now, and also we've been given the speed of sound in air in that particular day, which is 340 meters per second. Okay, so let's go to 2.1. It says, as the car passes, the detector records waves A and B, right? So the waves, they are recorded as follows: is air pressure versus time. Okay, both A and B, air pressure versus time. So now as we can see, waves A and B, they look a bit different. Okay, so now let's proceed to view the questions. And now there we can see 2.1.1. we have a question that says, which graph between A and B was recorded as the police car was moving away from the detector, and give a reason for the answer. We have 3 marks there. Okay, so now let's go back to the statement. Okay, so now, as the police car passes, the detector records waves A and B. So here we have 2 waves, we have A and B. So the question asks that which graph between A and B was recorded as the police car was moving away from the detector. Okay, so now I want us to highlight some few things and to remember some few things. Okay, so now remember that as the car, as the sound source is moving away from a detector or an observer, the frequency that will be observed will be less than the frequency of the waves emitted by the sound source. Okay, so now we are looking at a graph which shows a low frequency recorded as the sound source was moving away. Okay, so now, but here we don't see any frequency directly, but we see what? We see time. Okay, so we can see time here. So now in both graphs, this one, the time, it starts with what, I can see there the intercept, the t-intercept there is 0.1. There I have 0.2, there I have 0.3, and this one is the first one other than the 0 is 0.3. Okay, so now remember I've told you that the graph which shows the compression of a wave will have a higher frequency, and the one which shows a stretch of the wave will show lower frequency. This one will show higher frequency, this one will show lower frequency. So now A will show higher frequency and B will show lower frequency. But then why? If you can check here, because we have time, so frequency, how is it related to time? It's related to time while we use this this formula for this equation for frequency and period. So now the longer the period, the lower the frequency. So if we can check here, let's check our period. Here our period is what? Is 0.2. Our period is 0.2, and in this graph our period is what? Is 0.4. So the period on graph B is double the period of graph A. So the period in graph B is longer. So graph B has a longer period, and graph A has what? Shorter period. Okay, so now lower frequency. Now we only observe lower frequency as the source is moving away from an observer or a detector. Okay, so our answer will be B. Okay, so now what is the answer? Solution, let's take a nice colored pen. Let's take the lemon. Okay, so now the solution, our answer will be what? B, graph B. Why graph B? So now graph B, it has what? Longer period and lower frequency. Longer period and lower frequency. So now you have your 3 marks. You have one mark for the correct answer and 2 marks for the reason. Longer period and what? And a lower frequency. Okay, so if your graphs were, you were given air pressure against distance, we were going to compare these graphs using wavelength, but now we're given time, so we are using period. Keep that in mind. Okay, now let's go to 2.1.2. So in 2.1.2, they say calculate the frequency detected when the source was moving away from the detector. So now we know that the graph recorded when the source was moving away is graph B. So now we can use the information from graph B to calculate the frequency detected when the source was moving away from the detector. So what are we going to do now? Which formula are we going to use? Okay, so now we are going to use this formula. Frequency is equals to the speed of sound over the wavelength. We have derived this formula on the revision video. Okay, so now the frequency, remember they've given us the speed of sound as 340 meters per second, right? Okay, so but notice this, we are not given a wavelength, right? We are not given wavelength. So because we are not given wavelength, this formula will prove to be useless to us. Okay, so there's another formula that relates frequency with what? With period. Okay, so we will use this one. Okay, so we could have used this formula if we were given a pressure against distance, but now we are only given period, so we will use this one. So now we have 1 over 1 over the period. What is the period? It's 0.4. 0.4, remember, is 0.4 times 10 to the power minus 2. That is our period. So 0.4 times 10 to the power minus 2. So when I punch my calculator, I get a frequency of 250 hertz. Okay, frequency of 250 hertz. So now how is this going to be marked? It's going to be marked like this. The formula, substitution, and answer with units. If your answer does not have units, you're going to forfeit the mark for the answer. So now let's go to 2.1.3. 2.1.3 asks as follows: calculate the speed of the car as it passes the detector. Okay, so they want the speed of the car as the car passes the detector. So now, before we can do anything, let's write the formula for Doppler effect. So the formula for Doppler effect is FL is equals to V plus minus VL over V plus minus VS. Okay, multiplied by Fs. So now let's identify the data that we have. So the data that we have frequency of the listener, which is frequency observed by the detector as the car was moving away from the detector, which is the one we just calculated in the previous question. So now let's name it FL2, right? Let's name it FL2, and then we say FL2 is what? Is 250 hertz. Okay, so we have the frequency observed by the detector as the car is moving away from the detector, right? So what about V? We have V. They've given us that V is equals to 340 meters per second. Okay, what else do we need? We need Fs. Okay, Fs, they've given us Fs. They say that Fs is what? Fs is, it's not this one. They say Fs is 380 hertz. Okay, Fs 380 hertz. 380 hertz. Okay, what else? What about VL? VL is equals to 0. What about VS? VS, we don't know. It's the one that we are supposed to calculate. Okay. So now, we can calculate the speed of sound, the speed of the sound source. Okay. So, but let's say now, okay, here I've given you too much information. Let's say they did not give you the FS, okay, and the FS was unknown. So now they wanted the speed of what? Of the sound source. Okay, so we are going to need FL1, which is the frequency of the sound, the frequency observed by the detector as the sound source was approaching the detector. Okay, so we'll first have to calculate that. FL1 will be 1 over T, which is 1 over the period of this graph. So the period of this graph is 0.2 times 10 to the power minus 2. 0.2 times 10 to the power minus 2. So how much will the frequency be? When I punch into my calculator, I'm getting what? 500 hertz. I'm getting 500 hertz. Okay. So now, because now I have what? FL1, I have FL2. So now I have two scenarios whereby the source is approaching and the source is moving away. So now, as the source is approaching and source moving away, okay, so I will have two formula, okay. So now the first formula is it will be V over V minus Vs. Remember, when the sound source is approaching, we have minus Vs, right in here. But what is this? When it is approaching, is what is VL1. So, and then in here we have what? V L2 is equals to V over V plus Vs. It is moving away now, plus Fs. Okay, so now we go and substitute whatever that we have, whatever data that we have. So FL1 is what? Is 500 hertz into 340 over 340 minus Vs. Okay, so minus Vs multiplied by whatever, multiplied by Fs. Okay, we can put Fs as an unknown, or we can put it as 38 as it is. Okay, let's say let's put it as Fs. Let's say they didn't give us the value of Fs, so times Fs, and then here how much do we have? We have 250 hertz. Here we have 250 into 340 over 340 plus Vs times the Fs. Oh, here there's a mistake. Equal sign, guys. I've seen this mistake with a lot of learners. 500 is equals to 250 is equals to, okay, Yes, so we have two equations now. I have equation 1, I have equation 2. So we can solve this equation simultaneously, because now I have one unknown, I have two unknowns, I have Fs and Vs. Vs and Fs. So we can solve two equations simultaneously. So now, what do we do? You use your maths to solve the equations simultaneously. So what I do is this, is that I multiply this equation by what? By the inverse of this. Okay, so I will multiply this equation by 340 minus Vs over 340, so that I will have 500 times 340 minus Vs over 340 is equals to 340 minus Vs over 340 times 340 over 340 minus Vs times Fs. Okay, so now what we do on the left hand side, we do on the right hand side. So now if you can check this one, 340 cancels 340. 340 minus Vs cancels 340 minus Vs. So on the right, I'm left with what? With Fs. So now, in here I have 500 into here. If I solve, I say 340 divided by 340, I have what? I have 1 minus Vs over 340, right, is equals to Fs. Okay, so even in here, using the same method that I've used here, I will have 250 is equals to 1 plus Vs over, come on, I'll have 1 plus Vs over 340 is equals to Fs, right? So now this is still my what? My equation 1, and then what? My equation 2. So now notice that both of these expressions, they are equal to what? To Fs. Okay, so now I can equate this expression with this expression. So let's go to the next page. So now I have 500 into 1 minus Vs over 340 is equals to 250 into 1 plus Vs over 340. Okay, so now how are we going to solve for Vs? So bottom, guys, brackets off, right? Brackets off. So we can multiply out the bracket. You will have 500 minus 500 divided by 340 Vs, isn't it? Okay, so is equals to 250 plus 250 divided by 340 Vs, right? So now variables one side, numbers one side. So I transpose this 250 to the left. So I'm having 500 minus 250 is equals to transpose negative 500 over 340 Vs to the right. So I'm having 250 over 340 vs plus 500 over 340 vs. So in here I have what? I have 250, and in here I have 250 plus 500, which is 750 over 340 vs. Right? So if I want to solve for vs, I'm going to multiply both sides with the reciprocal of this. I'm going to multiply with 340 over 750, even in here 340 over 750. What we do on the left hand side, we must do on the right hand side. So now we can see that 340 cancels 340, 750 cancels 750. Okay, so now we are left with what? On the right we are left with vs. Okay, so on the left I have 340 divided by 750, okay, all multiplied by 250. So we have a very unrealistic answer 113.33 meters per second, which is a value that is quite high. One, okay, 113.33 meters per second. So this value is very high. So in a test you will not be given such a question whereby you will get such a high value. So here we had to get this high value because of the frequencies, they are very low. So in such a question we need to use frequencies around maybe 1600, 1200, somewhere around that region. So yeah, so this was just an example. So what is important here is the concept. Okay guys, so according to our calculations this is the correct answer, but realistically this answer, this velocity, it's quite high for a car to move at. It's almost, it's equivalent to what? Equivalent to let's see, okay, so yeah, this is the answer that you'd get from the information that I've given you. So you'll notice that we get the answer because the frequencies that we got were low, right? So now in a question that we've been given by an examiner, the one that is from question paper, so this would be this actually will suit to be the speed of a jet. Yeah, the speed of a jet, right? Not the speed of a car per se. So yeah, because this car would have to be moving very fast. Okay guys, so we will do, oh yeah, before I forgot, so I want to talk about uh, I want to talk about the applications of Doppler effect. Applications of Doppler effect. Okay, so yeah, the applications of Doppler effect. Here are the applications of Doppler effect. Okay, so let me give credit to the author of this document. It was authorized by the Department of Education, Department of Basic Education, Limpopo, Sekhukhune South. This one, yeah, it's from the district, from Sekhukhune South. Credits to you, my superiors. So now the applications of Doppler effect. So the one that they like to ask in exams is the one, the application of Doppler effect in medicine, right? So to measure is to measure heartbeat of a fetus. So the instrument that they use is what is the ultrasound transducer, ultrasound transducer. So what they do, what they actually do, as we have seen even on TV, they take that instrument, they apply some fluid on your stomach, on the lady's stomach, and then they the detector listens to the sounds that are being made by the fetus, and then it measures the frequencies, and then it will tell you how the heartbeat is moving, and also to measure the rate of blood flow. All right, so this one of blood flow, human beings, it can be used on human beings and also animals. So the detector is also the meter, which is the blood flow meter, is also placed on the skin of the host, and then as the blood is flowing, it makes sound, the sound that we can't hear with our own ears, but the blood flow meter will detect the frequencies and the direction of the blood flow. And other uses of Doppler effect, it is used in speed traps to determine the speed of a vehicle. So now the devices that is being used is a radar device, okay? And also is used in ship navigations, also in submarines and stuff. So it's used for navigations, and the instrument is what is sonar, and here in speed traps is what the radar device. So please go and practice the Doppler effect. It's quite an easy topic. What you have to know, you have to know the definition of Doppler effect. You have to know how to use the formula of Doppler effect, and also you must be able to apply the knowledge from grade 10. You must apply it to grade 12 work. Okay, so I will do a separate video on treating question papers related to Doppler effect. Okay guys, thank you, keep well. Don't forget to like, share and subscribe.